First one I want to talk about. For the first table, what was the formula we came up with? R of t equals? Everyone buy it? 1000t plus 1000. These thousands mean different things. What is this 1000 right here? Yeah, that's a starting population. Started with 1000 and then we added some stuff. What is this 1000 right here? Yeah, increase per year, or the rate. So we gained 1,000 rabbits per year. We also happen to start with 1,000 rabbits, but they mean very different things. And what's the name of that kind of function? That's a linear function. Okay, then we came down here, and we came up with a formula that is certainly not nearly as comfortable as the one up above. Might have really taken some thinking to get a formula, but what did we come up with? 1,000 times 2 to the t. That was the pattern from the bottom row. That's the formula. This is a different kind of creature than any that we have studied. Is it linear? No. Is it quadratic? No, quadratic would be like a t squared. Is it a cubic? No, that would be a t cubed. For the first time in this class, where is the t? Where's the variable? It's in the exponent. And that's a completely different kind of function than any that we've looked at this semester. When the t is in the exponent, hello.
Do you mind if I hand up a couple signs for the emergency?
Sure. Of course. If the t is in the exponent, do you know what we're going to call that new kind of function? It's an exponential function. Okay. Calling it exponential is telling you where the variable is. It's in the exponent. Are you guys aware of this evacuation drill that's coming? There was a sign right outside the circle this morning. So I guess we'll say, what's that? I think it's Thursday, whatever that. Yeah, Thursday. So on Thursday, we are having an evacuation drill. Those kinds of signs will tell you where you are supposed to go. So wherever you are, if you are on campus at that moment, you're looking for one of those signs to direct you where to go. The point here is not to just evacuate randomly because it's Thursday at 10:30. The point is to evacuate when you are told to evacuate. And if you aren't told to evacuate, well, that's the kind of thing we'd like to know. If there are gaps in our evacuation communication efforts, if there's like a whole wing of the building that doesn't get the word, then we can fix that and we can make sure that we adjust in case this isn't the drill. So anyway, if you get a text message or a phone call that says evacuate, then do it. If somebody in the hallway says evacuate, then do it. But don't just leave until you are told to leave. Okay, so that's that. And one little thing here, what did we get for the 50-year population on this one? It's like 1 point. All right, so we'll say about 1.126. And then there was this E business. And then what followed the E? 18. I don't want you to tell me E18. E18 is calculator speak. People don't speak that way. What does E mean on the calculator? Times 10 to the power of. That little symbol means all of that. Okay? And it's your job to know if the calculator says E, don't write E. It means times 10 to the whatever. Okay, all right, so that is indeed a whole lot of rabbits, probably way more than the planet could support, right? Sam? I think E stands for exponent. Why is it 10? Why not 7? We use the decimal place. What does DEC mean when you see it in the front of a word like decimal? It means 10. Everything we do is base 10, right? So E is exponent using our natural base, which is 10. Okay, on the next page, we are going to jump down. Oh, sorry, I meant to say some stuff about these guys. What does this 1,000 right here mean? That's the starting population. What does the 2 mean? Why was it 2? Because it was doubling. Yeah, you're doubling the original and then you double every time. That 2 was not just a random thing, it was 2 because we were doubling. If the rabbit population tripled every year, it would be times 3 to the t. Okay, so next page. We'll come down to number 4. Did we have a reader yet? Yeah, we had Hazen. We'll go to Eric. No, Eric, you went already. We're going to Joe. Number 4. Okay, let's make sure that we understand that this is a generalization of the example we just saw. We looked at 1,000 times 2 to the t. That was our rabbit formula. What letter is the 1,000 in this new general thing? That's the A. What's the 2? It's the B. Okay, so we've got our general formula right here. The important thing is that the variable is where? Is in the exponent, it's in the power. Okay, this is our new kind of function here. It is called an exponential function. There are a couple of little detail things here where it says that the b is always positive and not 1. Not going to worry about. You can think about why that might be true, but we'll just leave it there. It's not that big a deal to me. And then there's some graphs down here, and I just want to be clear. Looking at this first example, it's p of t is 1,000 times 2 to the t. I got a real pretty graph here that I got from GeoGebra, but I really want to make sure you buy that this is the right graph. What was the starting population? 1,000. So that's the point, 0 years, 1,000 rabbits. How many rabbits did we have after 3 years? It was 8,000. Do you buy? Like, does it look like that could be at 3 and 8,000? Okay, and then after 4 years, how many did we have? 4 years and 16,000. So you could just plot all these points, and you'll see this kind of thing where it's growing. But what would you say about how it grows in the beginning compared to how it grows later on? It grows slow in the beginning. It's relatively flat. In fact, it's kind of 0 out there on the far left. But then what happens as you move to the right, it grows faster and faster and faster. And if you ever look at people talking about like CO2 levels and carbon emissions and the greenhouse gases and all that stuff, you'll hear the word exponential tossed around. And what makes exponential functions, these kinds of functions, scary is the graph. No problems, no problems, no problems, no problems. Oh, good God, what happened in the last 2 years? And this is what exponential graphs do, okay? And so I'm not denying or affirming anything about like science or politics or any of that stuff. I'm just telling you that these kinds of things are scary because the graph looks no problem, no problem, no problem, but then, and so it could be that if again, I'm not on a platform here, but like if this is, you know, like CO2 over here, oh my gosh, if that's the CO2 level there, and we are someplace in this part of the picture, then it feels like no problem because it feels like things aren't changing very much. But by the time you get to a place like this and you realize you're in trouble, it's kind of already too late. You're already on the place where it's growing at a very, very scary clip. Joe. Correct. Yeah, it's not just that the CO2 levels are rising, but that the rate at which they are rising is also rising. It wasn't like 1,000 rabbits every year, a constant rate of growth. It's how many rabbits did you, yeah, it's an exponential. So how many rabbits did you gain? How many rabbits did you gain in the first year? How many rabbits did we gain? 1,000. In the second year, how many rabbits did you gain? 2,000 more. In the third year, how many rabbits did you gain? You gained 4,000 in that third year, 4 times as many as you gained in the first year. So yes, the rate is growing faster and faster. Okay, let's come over to here. So it turns out for exponential graphs, there's really only 2 kinds, 2 flavors. There's this guy right here, which grows from left to right. And then there's this graph right here, which is kind of the opposite. It falls from left to right. And the thing that distinguishes the exponential growth from exponential decay, that's our word for falling, is just this magic number right here. Yeah, so I don't want to use the word fraction, but I do want to, but I think you're on the right track. What makes the 1/3 something that's decreasing, whereas the 2 is something that's increasing? It's less than 1. That's it. So I don't want to say fraction because like this one right here could be like 5/3, it's more than 1, it's still going to grow. It's going to look kind of like it does already. The 2 again means every year we double. Every year we have twice as many rabbits as the year before. What does the 1/3 mean? Every year you have 1/3 as many rabbits. And I don't even know if I would say cut by 1/3. Maybe that's the right thing to say. Maybe you're thinking the right thing. If I hear cut by 1/3, I feel like losing 1/3 of the population. Are we losing 1/3? Is that what it's doing? What fraction are we losing every year? If you have 1/3 as many things left over at the end of the year, you've lost 2/3 of it. Yeah. So every year it's 1/3 of what it used to be. So that's written down here. Exponential growth if the A, that is a lie. I don't know why I called it A. What did we call that number right there? They called it the B. I apologize on a Friday lying to you. That's a B. B and B and B. So exponential growth if the B is bigger than 1, exponential decay if the B is less than 1. That's pretty much all we need to know about graphing these two things. Questions on that? Okay, when you're ready, we'll go next page. Let's take a look at number 6. Ben? Okay, so there's a table of values, like a bunch of points. You could plot them. I'll do it very roughly over here. 0 and 4, 1 and 3, 2 and 2, 3 and 1, 4 and 1, something like that. So we got a bunch of points. And the question is it exponential? Well, I mean, it may or may not be, but perhaps, I mean, maybe it's an exponential. Is it an exponential growth or a decay if it's anything? It's got to be a decay. So are you looking for a B that's bigger than 1 or less than 1? Less than 1. Okay. But the question is, how do we find it? All right, so we go back to first principles, and first principles are this: f of x equals a times b to the x. If you see exponential function, that is your formula. That's the new mx plus b, is that, right? You just know line y equals mx plus b. You need to know exponential, oh, y equals a times b to the x. Okay, let's go ahead and pick this first point and plug it in. How much is x? 0. How much is f of x? 4.2. Plug that into this equation. So we're plugging 0 in, a times b to the 0. It's important that you understand what letter is 0. What letter is 0? It's the x. The x is the variable. It's tricky because there's a's and b's floating around and you might be tempted to replace one of them with 0. It's not, it's the x. But what is f of 0 according to the table? 4.2. Now, something really nice just happened, because how much is, it feels like there's not enough. There's one equation with two unknowns, a and b. But how much is b to the 0 no matter what value b has? It's always 1. Any number to the 0 is 1. So this equation becomes 4.2 equals a. Super. We just found a. Can you guys tell me what is it called, that point 0, 4.2? It's the y-intercept, right? Okay, I think we just figured out that the y-intercept is always the value of a. This magical number right here is always sitting right there. It is the y-intercept. You don't need to go back, but I'll just take a quick glance at this graph. What was the y-intercept for our rabbit function? 1,000. Was 1,000 the value of a in the front of our rabbit equation? Yes, not a fluke. It always happens. The a is always the y-intercept. So far, so good. Now we're going to pick a different point. You can pick any point you want to. I will pick this one, You could pick a different one. Again, we're plugging in how much is x. All right, so we've got f of 3. And how much is f of 3? 1.44. So we know our magic formula is up there in blue, a times b to the x. But a we already know. A is 4.2. We found it. Let's use that. 4.2. How much is b? We don't know it yet. It's still b. How much is x? 3. Everybody see the plugging in that we just did? Do a little bit of work. Feel free to use your calculator to help. Find b. We'll say to the nearest hundredth. Subtract. Divide. Divide by what? Okay, so we go 1.44 divide by 4.20 is b cubed. You can find that number on your calculator. And then how do we solve for b? Cube root, right? We need the opposite of cubing. Somebody with a calculator? About 0.7. Can you give me a few digits more? Oh, 0.699. All right. Let's call it 0.7. Questions on finding that? I give you something like this on a quiz or a test, don't forget to write your final answer. I'm looking for the function. It goes back up to the blue at the top. It used to be a times b to the x. Now it's going to have many numbers in it. How much was a? 4.2 times. How much was b? 0.7 to the x. That's the equation. Questions on that one? I decided to pick the point where x was 3. Did we have to pick that one? No. It would have looked different if we picked another point. But what would have been the same at the end? I would have solved a different equation. But what would have happened at the end? The same answer. We would have gotten b as 0.7. Doesn't matter which one you pick. It's going to be 0.7 if it's an exponential function. Okay, you do not need to do this, but I just want to show you again, you have this really nice calculator here. It can kind of confirm some of what we just figured out. If I type in 4.2 times 0.7 to the x, and I'm just going to check my table, starting at 0 and going up by ones. What am I about to see if I look at the table? We should see those numbers that we were given. How's it look? Good. Okay. Let's talk about drugs. Search. Number one. Number one. Okay, so what you guys are going to do, and this is kind of a big activity here, but you're going to fill in a lot of stuff in that table, and you're going to graph. And I'm going to give you one little time saver as you fill in the table. So first, going from 1,000 to 750, do we see how that happened? Every hour, your kidney can deal with 25% of that drug. It eliminates 25% of the drug. How much is 25% of the 1,000 that we started with? 250. And if you start with 1,000, and you eliminate 250, then how many are left over? 750. But there's a better way to think about that, and somebody actually just said it. What's a better way to think of it? Is a 3/4. Instead of thinking of losing 25%, let's think of how much is still there, 75%. In fact, it's the same thing we did when we had that problem about jeans and discounts. You guys remember? There was like a 20% off sale or something, and instead of thinking of 20% off, we said, oh, you pay 80%. Let's do it that way. So maybe better is to just take each number and multiply by 0.75 every time, okay? So fill in the tables, check with your group mates before you start plotting, make sure everybody's got the same numbers. In fact, don't go too far, because if you have one number wrong, then the rest of them after that are wrong. So check in with each other. You're going to graph, and you're going to answer the questions on the next page together. So the equation at the top, filling in the chart is fairly straightforward. Plotting the points is straightforward, and you get something we expected, which was this exponential decay thing. But coming up with a formula. So we know that exponential decay formulas are a times b to the t. That's what they're supposed to look like. A is the starting amount. What was it? It was 1,000 times some unknown b to the t. And what we had before when we did the rabbits was we didn't have a b here. What did we have? We had a 2, because the rabbit population doubled every year. Well, what's happening to our population, the amount of drug? It's not doubling every period. What's it doing?
It's decreasing by a certain percentage.
Right. So what percentage is still there at the end of every year? We're losing 25%, but what percent is still there? It's 75%. So that number right there feels like it should be a 0.75. Because every time period we're losing 25%, we still have 75% there. Unfortunately, this formula is not quite right. Because this would say that every hour you lose 25%. But it didn't happen every hour. How often did it happen? It was every 4 hours. And so a few folks came up with some way to figure out, okay, it should be t divided by 4. Some people had that intuitively. Iris came up with a way to think about why that's so that I had never thought of before, but I think it's really great. She thought about the graph. Well, maybe you can say what you said.
It's basically the same as it's a horizontal stretch. Same as all those changing functions. So you get basically divided by 4.
What do you guys think?
Inside is within the exponent.
If every hour we were losing 25%, then it would have just been what we wrote, just to the t. But we're losing it every 4 hours. So instead of having, say, the purple graph where you lose it every hour and it decreases really quick, it has to happen 4 times as long. Instead of every single hour, it happens every 4 hours. And so we get this kind of dilation type thing here. You need to stretch it so that instead of happening in only 1 hour, it happens in 4 hours. And how do you stretch horizontally by a factor of 4? First, are we talking inside the function or outside the function if it's horizontal? Horizontal was on the inside. Things on the inside are opposite of what I expect. If I want to say multiply everything there by 4, because that's what we're doing, we're stretching, what do I need to put inside the function if I want to say, if I feel like multiply by 4 is the right thing, then I need to say divide by 4. And so I really liked Iris's way to think of it. Inside of the function, up there where the t is, make it a divide by 4. One of my groups did not do it this way. In fact, a few different people said, wait a minute, I know how to find an exponential function. If it looks like 1,000 times b to the t, and I have a table of values, I can do some calculations to find that b. So if this whole 0.75 and t over 4 is not intuitive at this moment, we can do it this way. It's just calculations. What did we have after 4 hours? So this was t, and then the amount of drug was 750. Can't I use that and plug it in just like a point, like we did before with the other table? So if I plug it in, how much is t? T is 4 at that point. I just picked that point. b to the 4. And how much is f of t? 750. And couldn't we do some algebra to solve that for b? So I'll divide by the 1,000. And then what do we do to both sides? It's the 4th root, right? 4th root of 750 over 1,000. Now, if you did this t over 4 business, then you never did this 4th root stuff. So we're going to get a number that you have not seen before. Can somebody give that to me? 0.93. Thank you. 0.93. It's good. Let's write the formula. F of t equals 1,000 times 0.93 to the t. So then here's the question. Is this the same as that? They don't look the same to me. One of them, it's a 0.75. The other one, it's a 0.93. How could they possibly be the same? Yeah, there's kind of a difference here in terms of what the 0.93 and what the 0.75 represent. I saw a few people reach for their calculators. What could I do to see if those are the same? Couldn't I graph them? What will I see? Hopefully we'll see the same graph. And in fact, it's a graph you've seen before because it's the one you drew on the previous page. So I'll do this real quick. You don't need to do this, but you can if you want. If I go into y equals, I'll type in the first one, 1,000 times 0.75 to the, don't forget parentheses there, x divided by 4. The next one, I'm going to make it darker by hitting enter at the far left. 1,000, and I want to be really precise here. Tyler, do you have any more digits than 93? Anybody have more? Yeah, it was the 4th root of 0.75. Okay, that's probably plenty. To the, what did we have up there? We had t, we'll call it x. In theory, these are going to be the same graph if they really represent the same formula. One thing I do want to do is plug in a good window. Looking at your table from the previous page, what's the first t value? 0. What's the last t value? 52. Great. How about we go up by 4s? What's the bottom of the graph? What y value? 24. I'll look at it 0. What was the top? 1,000. What was the scale on your picture? Every 100 was the scale? Okay, let's give it a shot. That's the first version, the 0.75 to the t over 4. I made the other one thicker, so if it's the same, then we should see exactly that. Yeah, and you can use trace and find different points and see they're really the same numbers, same y values. And so I actually like both of these formulas in yellow, but for different reasons. I like the top one because the top one feels intuitive to me. There was nothing intuitive about the 4th root of 750 over 1,000, not for me anyway. But the top one feels pretty good to me. I like the 75%. That was kind of given in the problem. I like the t over 4. That's saying every 4 hours. The bottom one is not intuitive, but it's something I can follow. I can do this process. But now that we know 0.93, I really like that I know 0.93. This problem said that every 4 hours, what percentage of the drug is filtered out? 25% is filtered out every 4 hours, right? Can you look at that 0.93 and figure out what percentage of the drug is filtered out every single hour? How much? It's 7%. That 0.93 is telling you every hour you have 93% of what you had last hour. Where did the other 7% go? That's what was filtered out. And I think the only way to know that 7% goes away every hour is to do this. And this is kind of counterintuitive for me anyway. If I tell you that every 4 hours we're losing 25%, it feels like I can figure out how much happens every hour. What should I do? If every 4 hours you lose 25%, can't I just do a 25 divided by 4? No? If after 4 hours you lose 25%, doesn't that work out to 6 1/4 every hour? No. Yeah, there's a compounding thing. We're going to use that word in next class. But it feels like 6.25% is what should have happened every hour. But in reality, it was 7% happening every hour. And it's because exponential functions don't behave linearly. And that's what you're doing when you divide by 4, assuming that it's the same every hour. And go in the other direction. If I tell you that we lose 7% an hour, how much do you think we lose after 4 hours? It feels like if we're losing 7% an hour, then after 4 hours, 28%. Yeah, it's that the thing you're taking the percentage of changes. And in fact, you saw that in this table here as well. How much did you lose the first hour? How many milligrams of drug? 250. How many did you lose in the next 4 hours? You didn't calculate it, but is it 250? No. Is it more or less than 250? You lost less. You lost less. Why? Because there's not as much drug in your body to get filtered out, right? Your kidneys are going to work really hard in the beginning to filter out because there's so much stuff in there. But now that there's only 750, it doesn't have to work as hard. And it's not going to get rid of as much stuff. This whole exponential decay thing works exactly the same with like drugs, like prescription drugs here, as it does with alcohol. So if you take if you drink a beer, you can imagine this vertical axis is how much alcohol is in your body at the start. And then what's going to happen to the amount of alcohol as time passes? It decreases. Does it decrease in a straight line? Decreases in the same way this does. I don't know how fast our bodies process, but it's reasonable, maybe 7% an hour. 7% of the alcohol that's in your body right now will get filtered out over the next hour. Yeah, questions on that? Okay, so here's our segue into next class. I know not everybody had a chance to answer number 6, but can we get Katrina to read it to us? Okay, so we know the drug is decreasing all the time. In theory, it never completely goes away because if you keep having 75% in your body, then there will always be something there. But at some point, it becomes so small that the machines can't even tell it's there anymore. Yeah, and we're not gonna, we wouldn't feel any of these effects. But I know that I want 0.1 milligrams in my body, and I know that that formula, either of these formulas in yellow, tell me how much is in my body. I'll use the top one there, 1,000 times 0.75 to the t over 4. And what are we trying to solve for in that equation? T. And where is the t? It's in the exponent. How do we solve an equation where the t is in the exponent? Have we ever solved an equation where the t is in the exponent? Not in this class. But you can see that it might be good to know how to solve an equation where the t is in the exponent so you can find how long something takes. So the tool that we need to use to solve equations like that is one that we're going to develop over the next, well, right after the test. And it's called logarithms. Okay, and so I'm sure I'll say this again when we get there, but in order to solve an equation where the variable is in the exponent, you got to use logarithms. So at the moment, the only way you can solve that is by graphing two things on the calculator. What's the other thing I should graph on the calculator? 0.1, right? Horizontal line, it's going to hit the graph at some point, and we can intersect. I might need to change the window here because it's going to take longer for it to happen. If I go out 200 hours, for example. And I think I might even have a hard time seeing if I look between 0 milligrams and 1,000 milligrams. Where's 0.1? It's right there on the 0 line pretty much. So how about we just go 0 milligrams to, say, 2 milligrams. What are we going to see for most of the left-hand part of this graph? Nothing. Where's the graph? Way off the top of the screen. But now I can see my point of intersection. And so you can find that by using intersect. Soon enough, we'll be able to solve that algebraically, which I know will let you sleep better at night. Okay. Have a good weekend. We'll see you guys Monday.